In this lesson, we're going to do an example work problem. So here's the problem. How much work does a hiker do carrying a rock up a 10-meter hill to his campsite? How much work does gravity do on the rock? What is the net work done on the rock? So, three things: work done by the hiker, work done by gravity, and the total work or the net work done on the rock. So, I'm going to start with a picture. Now, the information given didn't actually say how long the hill was, just that it was 10 meters high. So, here's my hiker carrying this rock up to his campsite. Now, first things we have to do is figure out what forces are acting on the rock. The camper is, we're going to assume, moving at a constant rate up this incline, whatever this hill is. So there's no acceleration here. We're just moving this rock at a constant speed. So then there's two forces that act on that rock. There's the force due to gravity, pulling straight down, and there's the normal force pulling straight up. Those two forces balance, so the only force the hiker is exerting is upwards against gravity. But the motion of the hiker is actually along the incline. So that means when we go to apply the work equation, remember work is force times displacement times the cosine of the angle between them, we're going to find the work done by the camper. Now the camper only exerts the normal force, or the hiker I guess, and gravity is pulling straight down. So let's first find the work done by the hiker. So I'm going to call that WH. That's equal to the force the hiker exerts, which is equal to Fn, times the distance the hiker walks, which would be the distance from the bottom of the hill to the top of the hill, which would be d, times the cosine of the angle between d and the displacement and the force. So if I draw that in, the displacement is this way, the force is that way, so we're looking at that angle. Now that angle is also this angle. And if you just complete this triangle a little bit, you can see that this displacement is parallel to this surface, and you can see that this is perpendicular, and so these are essentially alternate interior angles of a parallel line cut by a transversal, which means whatever length d is, that would be this side, d cosine theta, okay, is adjacent over hypotenuse, right? Cosine theta is the adjacent side divided by the hypotenuse, but the hypotenuse is d, so d cosine theta is the adjacent side. And so what I can see here is the work done by the hiker is equal to the normal force times d cosine theta, which is just the height that the hill is, which is 10 meters. And the normal force in this case would be equal to the mass of the boulder, and I wasn't told that, so m times g times 10. So let's say it was a 15 kilogram rock, then this would be 15 times 9.8 times 10, and that would be 147 newtons. Not newtons, Newton meters, which, because we took force times distance, which is actually a joule. So 147 joules. That's how much work the hiker did moving the rock along the hill up to the top. Now what's cool about that is it didn't matter what this distance was. It only mattered what that distance was. The displacement of the boulder, d, times the cosine of the angle theta, which I also didn't know, got me the height 10 meters, which I did know. So only the force that's actually in the same direction of the motion does work. And since the force was up, the motion was up, so I took the 10 meters up times the force, and I got the work done by the hiker. Now I'm also supposed to find the work done by gravity. So same thing, the work done by gravity is equal to the force due to gravity times the angle between gravity and the displacement. Now that's this angle here. I guess I should not call that theta, let's call it phi. So this would be Fg times d times the cosine of phi. But there is a relationship between this angle and that angle. And that relationship is, of course, 180 minus theta. So this is equal to F times G times D times the cosine of 180 minus theta. Now what that does, if we look at a cosine curve, the 180 minus theta tells us we're 180 degrees away from where we were. So if this is 0, then this is 180. And we can see 180 degrees is the opposite. It inverts it. So this is the same thing as the negative of cosine theta. So this equals negative FGD cosine theta. Well, we already know d cosine theta is the 10 meters. So this is equal to negative Fg, which is negative mg, times d cosine theta, which is just our 10 meters. And so this is equal to negative 147 newtons. You'll notice that's not newtons, that's joules. Gosh, I did that twice now. Joules. 147 joules. The work done by gravity is the exact opposite of the work done by the hiker. And that makes total sense because these two forces are balanced. There is no acceleration. The distance is the same. Gravity was pulling down as the rock was going up. So these two forces were opposite. So gravity did negative work. And so that means the net work done would be the negative 147 plus the 147, which equals 0 joules. So the net work done on the boulder was 0 joules. That doesn't mean the hiker didn't do work. The hiker still did 147 joules of work on the boulder. It's just that gravity did negative 147 joules of work on the boulder. So the net work on the boulder was 0. And we could have made that whole thing simpler by just saying, well, the net work is equal to the net force times the distance times the cosine of the angle between them. Well, if I look at the net force acting on the boulder, it's 0 because it doesn't accelerate, and so this would be 0 times it doesn't matter. The answer is 0. So the net work is 0 joules. Doesn't matter if I do it by adding up the work done by the individual forces or if I use the net force to find the net work. But it is interesting that work can be done even though the net work is 0.